My name is Sarah, and I'm a PhD candidate studying microbiology and biochemistry at UCSF. Prior to graduate school, I taught English and science in Spain and did post-baccalaureate microbiology and immunology research on tuberculosis at the University of Washington. In addition to doing tuberculosis immunology research, the year before graduate school, I worked part-time for an environmental education nonprofit. One of my favorite activities was digging through soil with children and families. They loved using magnifying glasses to examine our findings of worm eggs, millipedes, and white networks of root-like fungal hyphae. My current graduate research focuses on similar fungal hyphae, which are able to cause disease in humans. Pathogens are only a small minority of the hugely diverse set of fungi. Most fungi play an essential role in nature, degrading organic matter so that it can be recycled into new food. They grow in diverse shapes, from unicellular yeast to multicellular hyphae or complex mushrooms. Fungi help us humans make food and medicine. However, fungal pathogens can also cause life-threatening disease, and fungal infections are often particularly difficult to treat. Some fungal pathogens are thermally dimorphic, meaning that they grow in different shapes depending on temperature. These pathogens, including Histoplasma capsulatum, grows hyphae in the environment, which can aerosolize and be inhaled by mammals. Once inhaled, they sense the host's body temperature. Body temperature causes Histoplasma capsulatum to shift from growing as root-like hyphae to growing as pathogenic yeast. This pathogen is a source of approximately 500,000 infections per year in the United States. As temperature sensing is an essential element of their ability to cause disease, I'm interested in how these pathogens are able to sense temperature. I'm particularly curious about molecules that may act as thermometers, responding intrinsically to changes in temperature in a way that the pathogen can read and respond to. Molecules can respond to temperature in a variety of ways. One of my favorite hypotheses is that there may be molecules in this pathogen that can change in shape in response to temperature. One very extreme example of this that you may be familiar with is what happens to proteins in cooking eggs. Individual proteins that are separate and tightly packed can denature in response to heat and form an interconnected web of proteins. This happens to many proteins in cooking eggs, making them solidify. I'm currently investigating molecules that may change in shape or behavior in response to temperature in the pathogen Histoplasma capsulatum. There are a few molecules that I'm particularly curious about exploring, including the signaling mucin MSB2 and the RIP transcription factors. I'm also working to identify additional proteins or other molecules that may act as molecular thermometers. Please feel free to look at my poster or come talk to me if you're curious and would like to learn more.